of B or minus, the inversion of configuration is still partially takes place more often than the negation of configuration, resulting in a partially this. Is this clear? Yes, I didn't go through the molecular orbital theory because we are trying to skip that part in most of the throughout the process. A little more difficult to assimilate that. Yeah, they essentially give you the ideas of how the orbitals are changing, because when you change the hybridization of the sp3 carbon to an sp2, followed by again going to sp3, the orbitals are changing in terms of the hybridization state and also their ability to overlap. So it's a more complicated process. There's also the issue of highest occupied molecular orbital and the lowest unoccupied. That those are the interactions that are critical. But we avoided going through that. Now, solvent plays a critical role in many of these reactions. When we talk about that, first let's try to figure out what kind of solvent we normally deal with. Okay. So the solvents are broadly divided into two groups, so polar and non-polar. So let's say non-polar, and then polar solvent. And the polarity is determined, as we have already talked a great deal about dipoles and so forth. But the polarity is often determined using a method which determines the dielectric constant. Okay. What is the dielectric constant? It's given a big symbol, epsilon. So the dielectric constant is often used to give you a numerical measurement of the polarity of a solvent. Okay. And what really it means is that if you have a polar compound, how efficiently the solvent can interact with them, that is what is determined in the dielectric constant. So in vacuum, dielectric constant is given a value of 1. And if you get really non-polar solvent, like hydrocarbons, let's say gasoline. Gasoline has a dielectric constant of 1. Sorry, gasoline is about 2. Okay. In vacuum it's 1, and it's very close to that, extremely non-polar. Likewise, if you take hydrocarbons, hexane, pentane, and so forth, they are very non-polar. Hexane, pentane, they all approximately in the range of about 2. These are extremely non-polar solvents. If it is slightly polar, but yet very non-polar, that includes diethyl ether. So diethyl ether has a value of about 4. And essentially, we can also see others, such as acetic acid. Which has a value of about 6. These are all very non-polar solvents. In fact, the cutoff line that is considered is about 15. Okay. Anything below 15 is considered very non-polar. And of course, you have polar solvent where the dielectric constant increases. It could be 30, 40, 60, 80, and so on. Okay. So one of the most polar solvent is, of course, water. Water has a dielectric constant of 80, 78, in that range. They vary depending on the temperature. So that's the range where we look at. Now, again, another division is done, which is we call protic or aprotic. So in case of non-polar solvent, most of them are actually aprotic solvent. So all the ones that I discussed, like the gasoline, hexane, betaine, diethyl ether, gasoline is a mixture of both bunch of hydrocarbons. They are all aprotic solvent, aprotic non-polar solvent. Whereas acetic acid is an example of protic non-polar solvent. And on the other side, you also have polar solvent that could be protic or aprotic. The protic solvent includes something that can hydrogen bond. Okay. Therefore, we include water and all the alcohols, the methanol, ethanol, and so on. Typically alcohols. These are examples of polar protic solvent because they are ability to hydrogen bond. Ammonia is also considered protic solvent because that can hydrogen bond not as efficiently as with the oxygen. Nevertheless, that will be also. And the polar aprotic solvent includes dimethyl sulfoxide, DMSO, dimethyl formamide, acetonitrile. These are the examples of that. And again, these are all have very large dielectric constant. Okay, water is the highest, but formic acid is the second one. Formic acid is a polar protic solvent. But it has a very high dielectric constant, like 58. So broadly, therefore, these distinctions are important to understand. We do everything with respect to dielectric constant and their ability to hydrogen bond. Those are the two issues that we are mainly concerned. And why they're important? Because let's look at an SN2 reaction. If we look at an SN2 reaction, it's a one-step reaction. This is an action displacing that. In SN2 reaction, if you provide, of course, they are very, very weak in case of, first, before I get to SN2 and SN1, there one important thing that you need to know is that the first criteria is, of course, to dissolve both of them, the reagent and the nucleophile, in the solvent. Because sometimes what happens, you have a situation where the solvent, like a non-polar solvent, would dissolve the Rx if you have a long chain in the R. And the polar nucleophile may not dissolve in that. So what happens then? No reaction will take place if you have two completely different solvents, right? So it is important that you have to recognize that they must be dissolved in the same solvent. So in such cases, if you use, let's say this is dissolved in ethanol. But the sodium hydroxide does not dissolve in ethanol. It dissolves in water. Then what you do, you can make a mixture of ethanol water and carry out the reaction in those cases. That's why it is important to recognize that you need a solvent where both of these soluble. Now the second issue is, of course, where the reaction will take place best. And if you have a protein solvent, one of the consequences of that, the OH minus, as in this case, will be surrounded by the solvent molecules, and that is going to form hydrogen bonds, essentially reducing the nucleophilicity. So in protein solvent, the nucleophilicity of the anion, or whichever the attacking species, is reduced in a protein solvent. And therefore, you don't want that. That will reduce the rate of the reaction as well. And so ideally, for SN2 reactions, polar protein solvents are the best. Same sort of argument, if we look at SN1 reaction, consider that there is formation of a cation, an anion also. So in SN1 reaction, because we are forming a cation and anion, what really happens is that you would much rather have them hydrogen bond with the solvent, and the solvation really lowers the activation energy very. So the solvation the energy of activation on the reactivity state is reduced in the case of polar protein solvent. So if you didn't have a protein solvent, let's say the energy barrier is this much, and when you use a protein polar solvent, then it goes down, and therefore the reaction goes much faster. So that is much more beneficial because you form a ion pair, including a cation and anion. Hydrogen bonding lowers the energy of the process, essentially helping the reaction go faster. So those are the two bottom line of our discussion of the solvents, that in case of SN2 reaction, you want a polar protein solvent such as DMS or DMF, formic acid, etc. Sorry, not formic acid, but DMS or DMF, acetonitrile, those are the polar protein solvents. And in case of SN1, you want a polar protein solvent, which includes water, the alcohols, and formic acid, etc. Okay. All right, so I'll stop here today, but I'll go over the practice problems that I gave you.